Okay, so the third example I'm going to go through, I've taken this from a past paper. I don't know if I've got written down the 2017 past paper, which would be AS. So this question, there's two parts to this question. We've got the reaction, which is P plus Q going to 2R. So the information it's given you, 1 mole of P and 1 mole of Q were mixed. It's given you a volume of 1 decimeters cubed, which is really handy. And at equilibrium, X moles of P had reacted. So part A, deduce in terms of X the moles of R in the equilibrium mixture. So let's do that. That's a really easy one. So let's do this Rice table. Okay, and we've got our reaction P and Q goes to 2R. So our initial concentration, I always say concentration, the initial moles of P and Q is 1.0, 1.0. And we've got X moles of P had reacted. Okay, so we're not given how much of anything has reacted. So P, the change is going to be X, and we've got a 1-to-1 ratio. So the change is going to be X here, so minus minus. So equilibrium moles is going to be 1 minus X, 1 minus X. Here we started with 0. The stoichiometry here is 1 to 2, so our change is going to be 2x plus 2x. So our equilibrium moles is going to be 2x. So the answer to question 1, deduce in terms of x, the moles of R in the equilibrium mixture, is going to be 2x. That's the answer there. So the second one's a bit more confusing, well not confusing but complicated. At 298K, the value of Kc is 3.6. Calculate the equilibrium concentration of R in moles per decimeters cubed. So we want the equilibrium concentration here in moles per decimeters cubed. We want 2x, but in moles per decimeters cubed. So it involves just the same as we did in the last example. Lots of rearranging formula. So let's write out the Kc expression. Excuse me. So we've got 3.6, and the really good thing here, which I should have pointed out in the last video, is that it stated Kc, it stated the temperature, which the question should always state the temperature of Kc because Kc is temperature dependent. So let's fill this in. So we've got products, so the concentration of the product, we've got 2x, that's the equilibrium moles, over the volume, 1.0, and that is all squared. If you remember from, and if you don't remember, go back to the first Kc video. We use the stoichiometry when we construct the Kc expression, and we raise the concentration to the power of the molar coefficient. So we've got 2x over 1 squared, and then all over, so the reactants, so we've got 1 minus x moles over 1, and then we've got 1 minus x moles over 1. Now, the really good thing here is that the volume is 1 moles per decimeter, is 1 decimeter cubed. So we can actually get rid of all that, all the ones. So if you just rewrite that, we've got 3.6 is equal to 2x squared. I'm going to put it in brackets just to make it easier to look at. 1 minus x, 1 minus x, and of course 1 minus x times 1 minus x is 1 minus x squared. Right, so we have to start rearranging this equation. So what we're going to do, what I want to do is, first of all, we can turn 1 minus x into 1 minus x squared, which is great, just to make it a bit easier. So now I want to get rid of everything on the bottom, so I'm just going to times both sides by that. So 3.6 times by 1 minus x squared is equal to 2x squared. Now, we want to get rid of the squares, so, well, we want to get rid of the powers. So we do that by taking the square root of both sides. So by taking the square root of both sides, we end up with the square root of 3.6 times by 1 minus x, we keep it in brackets, is equal to 2x. That's got rid of the squares on both sides, but of course you have to take the square root of 3.6. Okay, so the next stage is you can do the square root of 3.6. So the square root of 3.6 is 1.9, and then 1 minus x is equal to 2x. Okay, and then we want to get rid of these brackets. So we're going to have the same as we did in the last video, just times everything in the brackets by 1.9. So 1.9 times 1, 1.9 times x. So we've got 1.9 times 1 is 1.9 minus 1.9x is equal to 2x. Okay, so then we want to get all of the x's on one side of the equation. So we can just add 1.9x to both sides. So 1.9 is equal to 2 plus 1.9x, that's 3.9x. Okay, so the next thing we want to do is we want to get x on its own. So we can do that by dividing both sides by 3.9. Divide that side, divide that side. So 1.9 divided by 3.9 is equal to x. And then the number I've got for that then, 1.9 divided by 3.9, x is equal to 0.49. Okay, so our x is equal to 0.49, so that's all fine. So we're calculating the equilibrium concentration of R in moles per decimeters cubed. Now our equilibrium number of moles is 2x. So we've got 2x is 0.97 moles. We've got 0.49 times 2 equals 0.97 moles. And then if we want it in moles per decimeters cubed, is concentration is moles per decimeters cubed, concentration is moles per volume, is 0.97 divided by 1.0 is 0.97 moles per decimeters cubed. So again, if you are happy rearranging equations, it's super easy and super straightforward. But you do have to get really fluent at that, so that part of your answering is really quick. Okay, so hopefully that makes sense.